Hello everyone, I am Milani. I'm currently doing a PhD between ArcelorMittal and MinParisTech, and today we are going to talk about the effects of matrix microstructure and second phase particles on the damage behavior of hot-stamped martensitic steels for automotive applications. To begin, the general context is about the reduction of CO2 emission via color whitening and also about more and more severe crash test criteria. The first graph represents for different countries and continents the evolution of CO2 emission per kilometer function of the year. This reduction can be assured partly thanks to light whitening of the body in one structure. Here is the typical application of pressed hardened steel in a body in one structure. These steel are hot-stamped martensitic boron alloy. This picture is an example of an automotive part during the hot stamping process. Our need is to improve the mechanical property of steel to lighten vehicle and still ensure crash resistance. We just talked about hot stamping. I am now presenting you in more details this process. Here is a classical representation of the thermal-mechanical treatment used for pressed hardened steel and their corresponding microstructure to the different steps. First, the austenitization between 900 and 950 degrees Celsius. Then we realize in the same step the forming and the quenching thanks to the press, which is water-cooled. And in third, the bake hardening process, which is a typical heat treatment of 170 degrees Celsius during 20 minutes. This process allows to obtain a high mechanical strength, but the ductility is also a key parameter to improve crash resistance. Crash ductility and bending test. Here is an action compression model representing a crash test. On the left, the numerical simulation, and on the right, the real mechanical test. You can see on this sample a succession of sheet faults due to the crash. That's why we use the bending test, which makes possible to study locally the capacity of steel to bend and therefore to make faults. It's a standardized test where a force is applied using a punch on a sheet metal. We draw the evolution of the load as a function of the displacement until a fracture criterion, which is a load drop of 16 Newton. You can then use finite element simulation to estimate the strength field at the apex of the bending sample. So to summarize, the bending angle at failure is determined experimentally. Then we can calculate the fracture strain in order to have an approximation of the crash ductility. This crash ductility can be influenced by several parameters. These parameters are, among others, the martensite property and the presence of second phase particle. In the martensite property, you have the role of the microconstituent refinement induced by prior austenitic grain size reduction, and also the effect of tempering, which is linked to second phase particle due to the presence of and the modification of iron carbide. In the second phase particle, you have the role of the titanium nitride inclusion. Likewise, we did two different studies. The first one is on the effect of tempering to evaluate the consequences of the different carbide population on damage, and the second one is about the inclusion and more precisely the titanium nitride inclusion to determine the impact on local ductility. Second phase particle can be represented via their size distribution. Here is a schematic size distribution graph between the number of particles and the equivalent particle size. The first distribution is a representation of the iron carbide with an average size between 0.1 and 0.2 micrometer. Our study number 1 will focus on this type of particle. Study number 2 will focus on the effect of titanium nitride inclusion, whose average size is about 0.5 to 2 micrometers. So we use two different studies to investigate the effect of this population on crash ductility. The first study is about the effect of tempering on crash ductility, where the main objective is to determine the influence of carbide distribution on martensite ductility for an equivalent tensile strength. We use steel with two different chemical composition, where the main variation is in the carbon content, as well as different thermal treatments to obtain different carbide population. We practice two austenitization cycles to obtain two austenity grain size, and there are four different tempering conditions from auto-tempered to 300 degrees Celsius during 20 minutes. Then the characterization, thanks to qualitative analysis of carbide via TEM on carbon replica, but also tensile test and bending test. We are first going to start with the evolution of tensile strength. On this graph, the evolution of the tensile strength function of the different tempering temperature for our two steels and two different heat treatments. We can see first that the grade 0.23 are the higher tensile strength than the 0.20 for a same tempering treatment. For all the conditions, there are a slight decrease of tensile strength up to tempering at 170 degrees Celsius, then it decreases sharply. We identify four different groups with almost same tensile strengths, but from different material and from different tempering temperature. The goal is to determine the variation of the crash ductility with a same tensile strength. We are now going to compare mechanical property group by group. Here is the comparison of tensile test curve for our four different groups with the same tensile strength. You can see on all these curves almost the same tensile strength for the two different steels in one group. On this four comparison, the grade 0.20 has mainly a higher elongation at failure than grade 0.23 for an equivalent tensile strength. However, the hardenings are almost similar when we compare steels in one group. In the same way, you have the comparison of bending curves for the four groups and for a same tensile strength in each group. These curves represent the load versus the displacement during a bending test. In all groups, the grade 0.20 has higher load to failure than grade 0.23 for an equivalent tensile strength. Thanks to these bending curves, it's possible to determine another key parameter in crash ductility, which is the energy absorbed by the material during bending. This energy can be estimated by the following law applied on a bending curve. During a crash, the material deforms by absorbing energy, and this capacity to absorb energy during a bending test is used as a criterion to compare the two grades. Here is the evolution of the absorbed energy in bending, function of the tensile strength for our four different groups. The first evidence to notice is that a higher tensile strength implies a higher absorbed energy. This is because tensile strength has a strong impact on the absorbed energy in bending. But for the four different groups at the same tensile strength, the grade 0.20 absorbed more energy during bending than grade 0.23. The absorbed energy is not just linked to the tensile strength, but also to the chemistry and other microstructural evolution of the martensite induced by the tempering. The absorbed energy in bending is now represented for all the different conditions and not just for the four groups. So you can observe the evolution of the absorbed energy versus the tensile strength. If you look at for a given absorbed energy, the steel with the highest carbon content had the higher tensile strength. This could be an improvement for anti-intrusion part due to the higher tensile strength. However, if you look the effect of the grain refinement due to the different heat treatment parameters, you can see that this refinement allows for a given chemical composition the increase of the absorbed energy. This could improve the mechanical part responsible for energy absorption in a crash. Another representation of the evolution of the energy absorbed in bending is in function of the tempering temperature. On this graph, the evolution for the two steel and the two heat treatments. The absorbed energy remains stable up to a tempering temperature of 170 degrees Celsius, then decreases sharply. Furthermore, for an isotempering temperature, the absorbed energy by the grade 0.23 is always higher than that of the grade 0.20. This is due to the higher tensile strength of the 0.23. We perform analysis on carbon replica with TEM. Qualitatively, some difference can be noted on the carbide size distribution. The first picture is taken from an auto-tempered grade 0.20, whereas the second one is after a tempering treatment of 300 degrees during 20 minutes. More homogeneous carbide distribution can be observed with the increase of tempering temperature. In addition to that, carbide size increased from 100 nanometers for an auto-tempered steel to 300 nanometers for the steels tempered at 300 degrees Celsius. So far, it's believed that this difference of carbide's population plays an important role on the damage behavior and on the crack formation, but finer analyses are ongoing to confirm this statement. We have focused so far on iron carbide. The second study of this presentation is about the effect of inclusion on crash ductility. The objective is to determine the influence of different inclusion distribution on the ductility of martensite. To do so, we use 0.3% carbon martensite steels with 3 different titanium content in order to obtain 3 different titanium nitride population and study their effect. We realized on each steel 2 austenitization cycles between 900 and 950 degrees Celsius to obtain 2 austenity grain size per chemical composition and just one tempering temperature, which is 170 degrees Celsius. The characterization was carried out on prior austenity grain size, then on tensile test and bending test, and also an automated inclusion analysis have been done. We begin with the evolution of tensile strength as function of titanium content. There is a low influence of the titanium content on the tensile properties with a heat treatment 950 degrees during 15 minutes, but a slight increase for the treatment 900 degrees during 7 minutes. The effect of the amount of titanium content on tensile strength is not very high, but remember that titanium may go into particles because it protects boron from nitrogen, so we can look at the population of titanium nitride inclusion. An analysis has been done via scanning electron microscope. This analysis was carried out on the 3 steels and is possible to represent the number of inclusion per millimeter square in function of their size for the 3 different titanium content. An addition of titanium induces an increase in the density of inclusion. Furthermore, these inclusions are mainly titanium nitride. The inclusion density is directly correlated to the nominal titanium content. For example, when the amount of multiplied by 4, the number of inclusion per millimeter square is also multiplied by 4. So the addition of titanium has a little effect on the ultimate tensile strength, but induces more inclusion. So what are the effects on bendability? This inclusion population comes together with difference in grain size, and here you have the bending angle at failure versus the prior austenity grain size. Despite coarse grain size, superior bending angle are achieved, and when we look closer to the inclusion population, we can observe that the high area fraction of titanium nitride seems to be detrimental to the bending performance. A general decrease in the bending angle with the increase in the surface area of inclusion can be observed. In conclusion on the effect of tempering on ductility at iso-austenitization and iso-tempering treatment, the grade with the highest carbon content absorb more energy in bending, since this is mainly governed by the ultimate tensile strength. On the other hand, for a given ultimate tensile strength is the steel with the lowest carbon content which absorbs the highest amount of energy before fracture. If you place at a given absorbed energy, the steel with the highest carbon content has the higher tensile strength. This could be a way of improvement for anti-intrusion parts. The refinement of the authentic grain size allows the increase of the absorbed energy for a given chemical composition, and this could, on the other hand, improve the energy absorption part. In summary, we are looking for a ultimate tensile strength which is maximum, with a carbon content which is minimum, together with Sparks refinement to enhance the absorption energy part in a crash. If we are looking for the anti-intrusion parts, we need a ultimate tensile strength which is maximum and a carbon content which is maximum too. Bendability being a less important criterion on anti-intrusion parts than on energy absorption part, the main characteristic targeted is the increase in tensile strength via carbon content addition. Now the effect of inclusion on ductility. We saw that 4 times more titanium percent induces an inclusion density about 4 times higher on our 0.3% carbon steel. 4 times higher inclusion density decreases the bending angle by 10% to 15% on the same steel. Low inclusion density plus Sparks refinement induce an enhance in bendability and consequently in crash ductility. This was Adrian Milani for ArcelorMittal and me in Paritech. I thank you all for your attention. If you have further questions, please contact me at the email address below.